Today we will solve the problem 3.13 of Griffith third edition, Introduction to Quantum Mechanics. The problem 3.13 is very interesting. We are going to prove that the expectation value of x is equal to integral pi star I h cross uh, delta over delta p psi tp. Here the interesting thing is we are going to find the expectation value on momentum based wave function. Pi is the momentum based wave function, and I h cross delta over delta p is the position operator on momentum basis. We have already seen that p momentum operator is equal to minus I h cross delta over delta x. That is position operator, momentum operator in position basis. Here just opposite. A position operator in momentum basis. Here the position operator in momentum basis is I h cross delta over delta p. We have to prove this. The we know the expectation value of x is equal to by definition the integral minus infinite to plus infinite psi star x psi star of x and t x psi star of psi x and t dx. Now what I am going to do is this first you take the psi x and t, which can be replaced using inverse Fourier transform. From inverse Fourier transform, we know psi of x and t is can be written as in momentum based wave function 1 over square root of 2 pi h cross integral between minus infinite to plus infinite e power I px over h cross p of pi of p and t dp. This is the uh, position based wave function. We are converting the momentum based wave function in terms of position based wave function. This is Fourier inverse transformation, you know it very well. So now what is psi star? Just this exponential term plus I will become minus I. That's all. This is the psi star of x and t. Actually, here you will get psi star of p star, psi star of p star t tp. Of course, this exponential term. So now you substitute it here. If you substitute it here instead of psi star and psi, you will get first you take this integral as it is. I am taking the first integral as it is. I am replacing the psi star psi by this integral. So it is integral minus infinite to plus infinite e power minus I p prime x over h cross psi star t p prime. I am labeling this as p prime and p to indicate that both momentum are different, and this one uh, this is the in the integral form. It is integral minus infinite to plus infinite e power ipx over h cross pi dp by dx. So we have converted this into momentum based wave function. This is actually the triple integral. We have to solve this integral, which we are going to do now. Now we got this triple integral for the expectation value of x. So I am rearranging the term. See, I am bringing this x. X is an operator. Remember that here x is an operator. I am bringing that operator inside this integral. So this will become x multiplied by this exponential term pi tp atx. So now I am going to differentiate this exponential term, of course, with the multiplicative factor minus I h cross delta over delta p, this exponential term. You can understand right now why I have introduced minus I h cross. So if you differentiate this with respect to P, you will get I H cross, then here Ix over H cross, Ix over H cross, uh, uh, that exponential IPX over H cross. Now you can cancel this H cross and this H cross. And the remaining thing is minus I into I will become plus 1. So here you have one x. So this will be simply x multiplied by this exponential term. So I can replace this x multiplied by say, this term by this one I h cross delta over delta p exponential I p x over h cross. So minus I h cross I have taken outside the integral. Then this is equivalent to x multiplied by this exponential term. So now we have to make further simplification over this. This is a triple integral. First, we will integrate this part first. That is a integral between minus infinite to plus infinite, delta over delta p e power I px over h cross pi dp. So here you adopt the UV method. So what will happen? Now you take this as u. Sorry, you take pi as u. This is u. So I have taken u as pi. Then what is tu? Tu in this case, I am. This is partial derivative. Pi depends on uh, position and time p of xt, and also we have to integrate with respect to p as well as x. So this can be tu can be written as partial derivative of p with pi multiplied by dp full derivative. This is by definition is equal to tu. That is deep. Du is equal to this one. So simply it will become pi because we have taken uh, u as pi. If you integrate, you will get naturally the pi. So this is the difference. If you differentiate this, you will get. And dv, I am going to keep these terms inside the bracket and dp because we are going to integrate over dp. So that as dv. So dv is equal to a partial derivative of momentum, the exponential term into dp. So then what is v? V is nothing but this exponential term. Now you use integration by parts. This is equal to uv. U is pi. V is this exponential term we have seen minus v du. V is this exponential term. Du is this one. Partial derivative of t with respect to p pi. Partial derivative of pi with respect to p into dp. Now here you have to apply the limit minus infinite to plus infinite. Remember that pi is a wave function. So the wave function vanishes at infinite, you know very well. So this will be equal to 0. So only this integral, second part of the integral exists. Now you replace it here in this integral. You replace this integral by this one. So already there is minus I h cross. So minus of minus will become plus. Plus I h cross integral this portion exponential I px over h cross and delta over delta p pi dp dx. So we have reduced it. Now what I am going to do is you separate this in terms of p and x. Here you have terms with x. Here you have another term with x. Only thing is here it is p prime and here it is p. So you take both, combine both. If you combine both, that is minus infinite to plus infinite e power I. Here it is plus p minus p prime over h cross. Of course, you have x dx. Here only you have x. So at this portion only we can do the integration with respect to x. And I have brought this 2 pi inside. Remember that I have brought it 2 pi inside in order to make this as a delta function. Here you have only the terms with p. Of course, psi star psi dp dp prime. So now we will simplify this further. Now we got this integral. You can carefully watch this integral in the curly bracket. This is the, by definition, this is equal to delta function, delta p minus p prime, that is argument of exponential term, delta p minus p prime over h cross. So now using delta function property, that is delta x by a, where x is variable and sorry, x is a variable, a is a constant, which is equal to a delta x. This is the one of the important property of delta function. Using that, I am bringing this h cross into the numerator. Now h cross and this h cross will get cancelled. And if you integrate the delta function, you will get uh, uh, non-zero value only when p is equal to p prime. So you can remove one integral. So the other integral will be minus infinite to plus infinite. This pi star I h cross delta over delta p pi dp. So we, because p prime p equal to p prime. So we are integrating only with respect to p. Now this is equivalent to x, operator x, because we are finding the expectation value of x. By definition, the expectation value of x is equal to pi star x pi, so tp. So here we have proved the expectation value, that is sorry, the position operator in terms of momentum basis is equal to I h cross delta over delta p, which is our aim. We have proved that it is I h cross delta over delta p is position operator in momentum basis. Thank you very much for watching my videos and supporting me continuously. Thank you very much.